Okay. Is that working? No, it is not. Can you hear me now? No. You might have to push this up. No, yeah, I got. Is that working? Oh, there we go. Modern technology. Well, again, my name's Kimberly Price. Many of you received numerous spam mails from me evangelizing BlueHat. I really do want to thank you for coming. It's a great opportunity for us to see some of the cutting-edge research that's going on in the community outside of Microsoft and recognize there are very smart people who don't wear the blue badge who we can learn from. So thank you for taking time out of your work schedule, out of your product, out of whatever you normally had planned to do today to come, and I hope it's a valuable day for you. Our next talk is Matt Miller, and he's got a very interesting talk. I think you're really going to like it. This is one of the talks that would fall in the cutting-edge research category, and I mentioned earlier during the break, during the executive sessions yesterday, condensed 30-minute sessions for the executives to see. We had Jim Alchin in the audience, and Jim actually interrupted Matt to say, "That's so cool." And that's a pretty neat thing to be able to say, that Jim Alchin thinks your talk is cool. So I hope you enjoy it. And at the end, I know Matt's going to do an excellent job of repeating questions from the audience so we can all hear them. And I'm going to turn it over to him now. Thanks.
Can everybody hear me? All right, thanks, Kimberly, for the introduction. I hope everybody wasn't too daunted by the title. I know it's a pretty weird one, and I'm sure that might have deterred a few people from coming, so I thank those of you who turned out for it. My name is Matt Miller. I'm going to be talking on the subject of temporal return addresses, and I'll try to help describe what those are as we go through this process and maybe make it a little bit more clear to those of you who are wondering what the heck I'm actually going to be talking about. So who am I? I'm actually probably going to identify with most of you guys. I do software development during the day. Don't actually do security stuff, although I do work for a VPN service provider. So that's my main job. But then on the side, I like to dabble in security stuff. I contribute to the Metasploit project in a number of ways. And I just do various research projects like the one that we're going to see today. And furthermore, do interesting research in the host-based intrusion prevention area on Windows. So just to give everybody a little bit of background on Metasploit, at the last BlueHat, you had H.D. Moore and Spoonham who came and talked about what the Metasploit framework was, some of the cool features of it. And just to kind of refresh those of you who may not have seen it, the Metasploit framework is an exploitation framework. Basic goal behind it is, the specific case is to write a framework that you can reuse to write exploits, reuse payloads, reuse the other aspects that you normally see in exploits, so you're not constantly cutting and pasting, and you're able to make reuse the code that you've written once for one exploit with all the other exploits you may write in the future. But that's not the actual focus of the project. The Metasploit project is really just a very research-oriented project. It's working on cutting-edge research technology that we in turn make public to the community. Try to encourage development, not just from us, but from people from the outside, get more ideas, and work more into trying to figure out some of the cool things that we can work on. For instance, later today, you're going to see a talk by Vinny Liu talking about the anti-forensics project that's now spoked off from the Metasploit project itself. So that kind of gives you an idea. We're not just working on exploits. We are researching anti-forensics and some of these other technologies. So the talk that I'm doing is just kind of an example of some of the random stuff that we come up with and we research and figure out whether or not it's feasible in the security realm. So that's kind of the introduction. Why don't we dive right in and see what we're going to talk about today. So the plan of attack. First thing that we're going to talk about is a brief background on return addresses. I'm not going to spend too much time on it, but just hope to get everybody on the same page as to what I'm talking about so the rest of the talk will make sense. And then after we'll talk about return addresses, we'll dive into what temporal addresses are, what they are, how you can use them, how to find them, and how you can actually use them for exploitation purposes. And then finally, we'll do a conclusion and talk about an actual case study where this can be applied. And this is in an area of memory called the Windows NT Shared User Data. And we'll talk about more details on that once we get there. So what do I mean by a return address? Well, a return address, in my definition, is basically something that you use in an exploit to gain meaningful control of execution flow. This is not necessarily limited to the typical overriding the return address on the stack, pointing it to some location of your shellcode, something along those lines. It's just some way, either direct or indirect, of gaining control of execution flow. The most obvious is the direct vector, where you're potentially overriding the return address with an address of shellcode on the stack or something along those lines. But there are also indirect means of gaining control of execution flow. For instance, using an intermediate instruction that in turn transfers control to your buffer, wherever it may be located. So for instance, an address of a jump ESP instruction that's located inside a DLL that's loaded into memory. Or other locations that may indirectly lead to control of execution flow. So that's the sense I'll be using the term return address in. What type of return addresses do people usually use? If somebody's writing an exploit on Windows, you'll typically see that they're going to make use of system and application DLLs that contain useful opcodes. For instance, they'll use a jump ESP if they're having a stack overflow and they want to transfer control after the exploit into the stack where their buffer that they control is so they can run arbitrary code. Furthermore, other opcodes that they use, depending on the vulnerability in question, is maybe they'll use a pop red if they're doing an SEH override or something along those lines. So one of the problems with some of this stuff, and one of the reasons why people don't typically use stack addresses directly, is that they contain null bytes, and they tend to be unpredictable between service packs and operating system revisions. So this is why you tend to see people on Windows using a more indirect means of gaining control of execution flow, such as by going through a jump ESP or a pop red or something along those lines. On Unix, maybe not as interesting to you guys, people will typically use stack and heap addresses pointing into shellcode directly, typically because stack addresses are much more predictable, depending on the application in question, on most Unix derivatives. So it makes it much more easier to use. They don't typically have null bytes because they're located towards the higher addresses in memory and things like that. And it's actually very rare, in my experience, to see people doing an indirect method bouncing through a jump ESP, something along those lines on a Unix derivative, but it's certainly possible to do this. And also, for exploitation purposes, it's not always necessary that you actually need to know an address. There are rather rare cases where you can have a purely addressless exploit. This is a great example in the Metasploit framework. There's an exploit for IceCast. And due to the nature of the vulnerability, you actually don't need to know any addresses. You simply send a buffer that, in turn, overwrites the return address with a pointer into a buffer that you already control, and therefore you don't need to know the address of anything. You just trigger it, and that's that. So that's a very uncommon case, but it is a situation where you actually don't need to know any addresses on the target operating system. So that's an interesting point. But in the very general case, most of the time, people are going to make assumptions on the address-based layout of the target process. They're going to assume that the jump ESP instruction is located at this specific address because I know that this DLL will be loaded at this address. And then, as I said, there are only rare cases where you won't need to know the address. Maybe it's automatically overwrites the return address for you or something along those lines. But typically speaking, you will need to make an assumption about the address-based layout in some regard. So in the case where that's necessary, if the address space is different, your exploit is going to fail. And that can be a problem. So one of the specific cases is if you are using a static address that you assume to be in a DLL or something along those lines, these addresses are often not the same between different operating system and application revisions. A good example is WS2 help DLL. This is one that we use extensively in Metasploit, and lots of other people who write exploits use as well, that actually has a consistent mapping address and everything between on NT, on 2000, on XP in 2003. The problem is that in between the major revisions, it actually doesn't have the same base address. And therefore, if you were trying to write an exploit that was going to target a bug that affected both 2000 and XP, and you were trying to return into an opcode in WS2help.dll, you actually wouldn't be able to use the same address because they're different between the major revisions. So that's one of the problems with using these static addresses inside DLLs is that you're subject to, they might change between an application revision or an operating system revision. So you're limited in that regard. So when you are writing an exploit, this is going to force you to have version-specific targets. I'm writing an exploit for vulnerability that affects 2000 XP 2003, but my return addresses vary between the platforms. Therefore, that means that I'm going to have to know the operating system version that I'm targeting when I go to exploit it. There are indeed cases, actually, though, where you can write an exploit that can be universal, affecting all of the platforms that the vulnerability in question is on, without having to use version-specific addresses in nature that would require you to determine the target's operating system or application version or things of that sort. A very good example of this is Metasploit's RPC DCOM exploit that, while it does use version-specific addresses, the nature of the way that things are structured between the different operating system revisions allows it to actually be able to be sent in one request and still work on all the different operating system revisions. So that is an interesting case of it, although commonly speaking, that's not the common case. So in some cases, though, you can actually determine the operating system version or the application version reliably. This is especially common in things like browser-based exploits, where you can use JavaScript or something like that to determine actually, what operating system they're probably running on or what browser version they're running on or something along those lines. But in other cases, it's also common as well. So in the case where you aren't able to determine the operating system version or the application revision, your target selection, I have a vulnerability that affects 2000 XP, but I don't know which one it is, it basically becomes a shot in the dark. So you're just going to guess, I assume that this target is probably running XP, I'm going to try this target. But if you're wrong, especially for things on Windows, although less the case on Unix with forking daemons, you will result in a lost opportunity if you use the wrong target because the application will crash. Maybe it's a system service and it will respond in 30 seconds or something like that. But generally speaking, it's going to result in a lost opportunity, and therefore you may not be able to get your attack to work. So the big question to ask ourselves here is there any way that we can improve this? Any way that we can make this return address usage more reliable, more universal, perhaps? So the answer is, well, we'll see. That's the point of this presentation. So the big question also is, can moving targets be useful? If you look at a process address space, just pop open a debugger, look at different things in it as it runs, break in at different points, you'll see that the process address space is in a constant state of flux. It's constantly changing. The stack, things are getting pushed and popped from the stack, calls are being made, all that sort of stuff. Local variables are being stored, things like that. Things are being allocated in the heap. They're being deallocated, freed, process heaps are being created, things like that. Furthermore, files are possibly being mapped into memory, maybe subsequently unmapped. Maybe the contents of the file are changing as the program runs. And furthermore, the obvious one is DLLs. They're being loaded into memory as dependent resources and things of that sort, and then maybe being unloaded when they're no longer necessary. So the broad picture is, if you look at it, it just seems like the address space is a very unpredictable beast. So when people are going about and searching for reliable return addresses and things like that for vulnerabilities, typically speaking, people will only look at what are referred to as the static regions. Although they may not be static between operating system version and revision, they are static for the specific target that you're working with. So, for instance, this typically is going to limit you to loaded images, DLLs, executables, things like that that are dependent for the program to run. So those, unless there's a patch or something along those lines, those will remain fairly static for that operating system version or application version. And there are a few other regions that people use sometimes, like the PEB and the TEB, that have predictable addresses and sometimes can be used to be leveraged as a return address and things of that sort. So this is typically what people are looking at when they're looking for return addresses. And the important question here is, are we missing anything important by not looking at these other non-static regions? Is there anything that we could possibly use in them? At first glance, you would think, no, there isn't. They're inherently dynamic. But as we'll see, that may not be the case. If you just think at a high level, these dynamic regions of memory may actually, at certain points in execution, contain viable opcodes. Things that you could use, for instance, a jump ESP that would then transfer control into your buffer or something along those lines. So a couple examples of these. Perhaps there's a pointer stored somewhere in the heap, pointing somewhere else in memory. And the bytes that compose the address of the pointer may actually contain viable opcodes. They may contain the bytes that in turn translate into a jump ESP or something along those lines. Another example, maybe there's an integer stored on the stack in the heap somewhere in memory that the integer itself, the value, the bytes that compose it actually are correlated to a viable opcode, such as a jump ESP. So these are cases where you could see a dynamic region actually containing useful information. The problem is that the state here is inherently transient. If it's being stored on the stack, if it's being stored on the heap, you probably aren't going to be able to reliably predict these values are going to be set to a certain thing at any one time. But however, there are certain transient states that can actually be predicted. And this is going to be the subject of this talk. A very good example of transient states that can be predicted are inherently timer variables. Things that are storing timer state somewhere in memory. And these are the things that I'm going to refer to as temporal addresses. So what is a temporal address? Temporal address, easiest example, right there. Time t foo, setting it to the number of seconds since 1970 epoch. I'm just storing the current time of the system in this local variable or wherever it may be stored. This is an example of just something that stores time or state somewhere in memory. It's a location, maybe it's storing the number of seconds since January 1st, 1970. Maybe it's storing the number of seconds since the program started. Some kind of periodic timer that's being updated with something that's relative to either an absolute time or some kind of relative time that you could measure. So when you break temporal addresses down, you basically identify that they have three properties. The first property is that they have a capacity. This is regarded as the maximum size in which a maximum amount of timer state that this address can store. So for instance, if you have a time t variable, that's 32 bits, but it's assigned integer, so it's going to be 31 bits. So that's the maximum amount of timer state that you can store within that without rolling over to to higher time or whatever. So that's what the capacity is. The period. This is going to be how often the temporal address is updated. How periodically you're updating, maybe every second you're updating this local variable to a new timer state. Something like that. And then lastly is the scale. And this identifies the unit of measure associated with this timer variable. As we've been saying, it's going to store perhaps the number of seconds since 1970, perhaps the number of seconds since 1601, a counter from program start. These different types of things, that is the scale. It identifies at what point that timer is being conveyed relative to. So the timer states, basically, they're just a series of bytes under, in a certain order. And knowing these properties of a temporal address can actually be very useful to us, as we'll see. The things that it allows us to do, we can predict certain things. We can predict when certain byte combinations will occur within the timer state. And furthermore, we can identify how long these byte combinations will last within the timer state. Since we know how periodically each of the bytes will be updated, we can then predict both of these combinations. This makes temporal addresses potentially useful as return addresses, because we can predict when certain byte combinations can occur, and we can predict how long they will last. So all we need to know is when these useful byte combinations will occur. So let's see how we're going to go about that. To give everybody kind of a concrete example of what a temporal address is here. On the screen I have described a temporal address that has a capacity of 4 bytes. The period is 1 second, so it's being updated every second. And the scale is measuring the number of seconds since 1970 epoch. So let's break this down a little bit. Let's say the temporal state within this timer variable reaches the number of seconds displayed on the screen. If we convert that to hex, we see the number displayed right over there. If we disassemble this, 2 of the bytes in it, we see that the 54C2 actually disassembles to a push ESP ret-in combination. So what this is equivalent to is it means that on Monday, January 9th, 2006 at 4:16 p.m., this address will contain a universal, assuming this address is predictable for every operating system version or whatever the case may be, it will contain a universal ESP to EIP transition. So that's basically what this breaks down to. But one of the gotchas here is that this can only be used for 4 minutes and 16 seconds. So, you got a little window of time there to work with it. So we've seen kind of with that previous slide, we've seen how these temporal addresses might be useful, but they're not going to be useful unless we can actually find some. And not only that, we have to find ones that are going to be universal. So how do we go about this? Well, first let's take what we know about temporal addresses. We know that they have a capacity, a period, and a scale. So how can we use this to identify them? Well, there are a few approaches you can go about this. I mean, there's the obvious one. Maybe I could sit down for a month, manually analyze the address space and say, okay, I found this region of memory that keeps getting updated at a constant time, but I really don't have that much time. So other things you could do. You could breakpoint on timer-related functions. You could see, maybe break on the time function and see where the output's being stored. That's not a bad approach, but you may miss things. And it's also very tedious, maybe a manual process. You could write a program to do it, but you may still miss things. But perhaps a better approach, and this is the one I'll be talking about here today, is you could use a program that will actually compare the address space differences over time to find patterns. And that's what we'll talk about. So let's focus on that. The most automatable way is going to be through differencing the address space over constant periods. So the way that this would work is a process's address space would be pulled in number of times, let's say 5. So I'm going to take slices of the address space 5 times. And furthermore, each of these pulling cycles, the 5 times that I'm pulling it, will be spread apart by a constant number of seconds or a period of time, so defined as t. So let's say 5 seconds. So that means I'll pull once, wait 5 seconds, pull another time, wait 5 seconds, and so on until I've completed all my pulling cycles. So each time a pulling cycle completes, we will difference the previous snapshot of the process address space with the current snapshot of the process address space. And what we'll do is we will say, okay, it looks like this location has changed at a constant interval over this period of time, and that period of time, the amount of change that was made within that variable is less than the polling cycle period. So what that breaks down to is after we flagged all these different addresses, we can go back and try to calculate their capacity period and scale based on the constant amount of time that they changed and maybe a couple other attributes that are involved in it. So let's say, for example, if an address had its contents incremented by 5,000 each cycle and t was defined as being 5 seconds, this could tell us that the period could be between 1 second and 1 millisecond, to give you guys an idea of how that might work. So here's an example of a program that I'll demonstrate here later for actually doing this process called Telescope. And what this will do is this will attach to a process and simply do the polling of the address space. And the output that you see here is this is a program that all it was doing, it was a while one and simply storing the output of time in a local variable. So, and then it was sleep for 1 second. So every second it was updating this local variable with the output of time. And as you see, it identified on the stack, those lower addresses or stack addresses, that there is a capacity of 4 bytes, a scale since epoch 1970, and the period being 1 second that was found at that location. So this could be used to identify that specific temporal address. And the other things that you see here, this program is not foolproof. It's just simply meant to help reduce the potential ones that you want to look through. So you may get some outliers and ones that you want to ignore, but it does reduce it quite substantially. And there are 2 other addresses that you see up there down below, and these are the ones that we're going to talk about later as being pretty interesting. So once we've found these temporal addresses, once we've used this program to find them, that's really only the first step. The next thing that we have to do is we have to calculate how long is it going to take for each of the bytes within the temporal state to change. And this is important, as you'll see. Basically, the way that this will go about working is we know that each byte has 256 combinations, 0 through FF. Calculating the iterations between each byte index x is simply described as 256 to the power of x, where the byte index starts at 0. So for byte index 0, we know it takes 1 iteration for that to change every time. So 256 to the power of 0 is 1, and so on. You do the math from there, and you get the number of iterations it takes. This is just a constant number, the number of iterations it takes to change each byte index. And then furthermore, if we know the period of a temporal address, we can calculate how long, in a matter of seconds, it will take for each byte index to change simply by taking the duration, the number of iterations for each byte index, and dividing it by the period. And that will produce the number of seconds for that byte index. So to give you guys an example of how this would work, we'll see that on the next slide. But an important note is these calculations are very important because this is going to be used to tell us which byte index we should start at. For instance, on this slide, this is a script that was written to generate these time intervals and do some other calculations that you'll see later. But basically, the output here was for a 4-byte capacity temporal address that's updated every second, and it's measuring the number of seconds since 1970 in the scale. And the output we see here is that we see that byte index 0 is updated every 1 second, as we would expect, because that period is defined as 1 second. Furthermore, byte index 1 is updated every 4 minutes and 16 seconds, and so on and so forth. The important aspect of this is that it will tell us which byte index we would want to start our search at for viable opcodes. The end goal here is we want to find a jump ESP or another instruction somewhere within the temporal state at a specific window of time. But in order to do that, we have to figure out where we want to start our search from. it really doesn't make any sense if the byte is changing every 1 second to use that as the starting point for our search, because there's no way in our exploit that we're probably going to be able to get a granularity of a 1 second window. It's just not going to happen. But more realistically, we may be able to get a 4 minute and 16 second window. That doesn't sound too infeasible. So in this case, the output tells us that for this 4 byte capacity, 1 second period, measuring the number of seconds since 1970 temporal address, we'll want to start our search for viable opcodes at byte index 1. So let's review what we have so far. We figured out that temporal addresses have a capacity, period, and scale. And we also know the duration of each byte within the temporal address based on that period. So what does that allow us to do? Well, now we can predict the future. So how are we going to go about doing that? Well, first, before we can predict the future, we want to try to figure out what is our viable opcode set. What are the opcodes that we can use maybe for the specific vulnerability in question or something else in order to leverage control of execution flow. I mean, the end result is we're using this as a return address. So there are only going to be specific instructions that we can use to take control. So maybe for the Stack Overflow, we're using a jump ESP or some other instruction. So we'll identify those opcodes, break them down to the actual bytes that compose the instructions, and we'll use those when we're doing our search. So once we've identified our set, we can simply use the attributes of the temporal address, as well as how long it takes for each byte to change, as well as our opcode set, to generate all of the possible permutations within the timer state that could be useful to us. So the algorithm to go about this, it's pretty simple. Basically, the way that I went about it is you take your viable opcode bytes and you plug them in at each byte index starting at the predetermined first byte index. So for the previous slide, we saw that we wanted to start at byte index 1 because it had a window of 4 minutes and 16 seconds. So we'd start plugging in our bytes at that position. So for instance, if we had a temporal address that had a 1 second period, we'd say, okay, well, I have a jump ESP, FFE4. Well, the first byte I'm going to plug in at byte index 1, and the second byte I'm going to plug in at byte index 2. And from there, I'm going to generate all the permutations that contain those bytes. So for instance, it would be FFE400, FFE401, and then so on and so forth. You generate all the permutations that contain those bytes. And furthermore, you go then on to the next byte index. You say, okay, well, now at byte index 2, generate me all the permutations that contain FF and E4. And that will then, in the end result, produce all of the timer states that will contain these viable bytes. So in the end result, at the very end, we have all of the timer states that we could possibly use that contain all these viable opcodes for purpose of exploitation. So once we've done this, after we've calculated all the permutations, well, now we have basically all we need to know, but we really need to figure out when to strike. I mean, this is all hinging on time, right? So we're going to have to figure out the time on the person's computer. So picking the time to strike. What we need to do is we need to know the location, or we know the future location and states of a temporal address, but we don't know the time on the person's computer. So what we're going to do is we're going to go about figuring out how to determine system time or whatever the unit of measure is that the scale is indicating. So for instance, if the scale for the temporal address that we're working with is measuring the amount of system time, or it's measuring system time, then what we're going to need to know is we need to know the time on the person's computer. Furthermore, if the scale is maybe measuring the number of seconds that occurred since the program started, well, then we're going to need to know when the program started. If we can't determine these things, then we're really not going to be able to make use of this stuff, because although we know when we could strike, we won't know actually what the window of time is on the person's computer to actually make this work. So the latter example here, measuring the number of times since the program started, that may actually be a little bit unfeasible. I mean, I don't know of a way that you could probably reliably determine, maybe application specific, how long it's been since the program started. But determining system time is actually very easy. I'm going to go through a few examples here, but keep in mind that the examples that I list are just tip of the iceberg. If you be creative, you could probably call somebody up and say, what time is it? And they'll come back and say, it's this. They're not going to be rude. So these are just some examples of how you can do it remotely without having to do some kind of social engineering. So one example is DCRPC. It has a function that you can call on the person's computer called netar remote time of day. And this will actually return things like the time zone, milliseconds, hours, seconds, all the things that you would need to be able to extrapolate what the time, what the current time is on the person's computer, giving you enough information to be able to predict when you should strike. Another great example, let's say you're trying to use an exploit in IIS or some other web server. Well, it's handy because the HTTP server will readily provide you with the date. All you have to do is connect to it, send a head request, and it'll tell you what the date is on that machine. So this is a great example of one that you could use if that's your specific target. There are lots of other ways that you can go about doing this. Just a few to list. ICP timestamps and IP timestamps. These don't actually give you the full time on the person's computer, but they do give you the number of milliseconds, I believe, since midnight UT. So that's the current day, the number of milliseconds that have elapsed since the current day. While that doesn't give you the higher granularity about the day, the month, all that stuff, you can probably be smart and say, well, I'm going to assume that the person has the day set correctly, but now I have enough information to determine the full time state based on the number of milliseconds that have elapsed since midnight. So you can use this partial information to build a complete picture and then use that for the purpose of exploitation. Other ones, people familiar with IRC, you can use a certain method of getting time through that as well. SSL negotiators are more than happy to provide time information, and the list really goes on. Be creative. There are a lot more that you could find. So this brings us on to the case study. And this is going to actually show you a real-world example of where the topic in this presentation can be applied. And this is going to be in Windows NT shared user data. So what is shared user data? A lot of people here might be familiar with it. I'm just going to describe it anyway, so bear with me. It's a shared region of memory that's going to be mapped into every Win32 process. It's located in every Win32 process, and furthermore, it's located at the same address in every version of Windows NT for every process. So this is great. This is the kind of stuff that people who are writing exploits love. They want stuff that's going to be at the same address for every instance of the process, for every target that they could possibly have. This makes it super easy. But generally speaking, shared user data doesn't really contain a lot of stuff. In some cases it does, but it doesn't actually contain a lot of portable stuff that you can use for return addresses universally. Or does it? Basically, some other attributes of shared user data is it's been executable up until XPSP2 with PAE or other hardware support for hardware enforced NX. So that means that Microsoft's doing a good job. XPSP2, the technique described in this presentation, if I were to try to return into shared user data and I was on a machine that support hardware enforced NX, I wouldn't be able to because it wouldn't be executable. And that's going to be a requirement. I am trying to execute instructions within the temporal state. So this is an instance where Microsoft's enhancements are doing a good job. So one of the biggest drawbacks, though, to this approach, aside from that, is that the actual address itself will contain null bytes, or one null byte, and it's in byte index 1. This is going to limit the scope of this actual specific case study because a lot of times, especially if you're dealing with a vulnerability in something that involves a string function or something along those lines, you won't be able to use null bytes in the buffer that you're sending across. So that can limit you, but it's still important to note that there are going to be exploits that don't have this restriction on null bytes. So the big question here is, what does shared user data have to do with this presentation? Well, that's because it contains temporal addresses. So let's take a look at shared user data. It's got a few attributes in it that are kind of interesting. It's got, first of all, if you look at the very start of shared user data, it has a tick count low attribute. And this starts, like I said, at the very first offset in the shared user data. If you analyze this as a temporal address, you'll see that the capacity is 4 bytes. The period is actually variable, which I'll describe in a second, and the scale is measured in milliseconds into boot. The period is variable because it's actually calculated against a multiplier that is determined based on hardware. So while, depending on whether or not you're using emulation or something along those lines, the period may be constant, it has to be, in my opinion, regarded as variable, and therefore you couldn't use it as a temporal address. And just as a sidebar, that's a very important thing to note. If you're trying to use this technique for exploitation, you have to know all 3 attributes, otherwise you can't make use of it. If you don't know the period, you won't know the intervals at which the bytes are increasing, and therefore you won't know the windows of time that you have to work with, or even when the values will be set to certain things. So it just makes it totally impossible. And it's the same for the other bytes, although capacity, perhaps, maybe, maybe not, just kind of depends. Next one, at offset 8 in shared user data, this is interrupt time. So the capacity here is 8 bytes. The period of this one is also variable, but the scale is measuring 100 nanosecond intervals of time processing or interrupts, I believe. Haven't been able to find verification of that. But the last one, and this one is the most interesting, is the system time attribute of shared user data. This is located at offset 0x14. Its capacity is 8 bytes. The period is 100 nanoseconds, and the scale is 100 nanoseconds interval since epoch 1601. So that one right there, we know all 3 attributes, so that could actually be pretty useful. So why does system time rock? System time stores the count of 100 nanoseconds intervals in 1601. Note that from my analysis, this does not actually appear to account for daylight savings time. So if you're in an area that's using daylight savings time, it just disregards that. The system time attribute itself is actually a k-system time structure. And the way that you look at this is just in WindowBug, pop it open. You'll see that it has a low part, a high 1 time, and a high 2 time. So this is just, you can think of it as a 64-bit integer for all intents and purposes. High 2 time is, from what I've seen, always equal to high 1 time. But maybe there's a case where it isn't. Not very important. So let's see how we can abuse this. What we're going to need to do first is we're going to need to use that script that we had to calculate the per byte durations, how long it takes for each byte index to change. And what that'll come back with for this 8-byte, 100 nanosecond interval measuring since 1601, it'll tell us that the first 3 byte indexes actually change faster than a second. Well, I mean, it is measuring in 100 nanosecond intervals, so it is changing very fast. And then the 3rd byte index changes a little bit more than a second. Still not useful for us, but the 4th byte index changes every 7 minutes and 9 seconds. So that's a pretty decent sized window. We can make use of that. And then even on to the 5th byte, you get a whole day to work with here. So that you're just increasing your feasibility by the higher you go up in byte indexes. So by looking at this, that's going to tell us that we should start at byte index 4. And this is going to allow us, for an exploitation window, a minimum of 7 minutes. So basically, the final step here is for system time, what we need to do is we need to generate the permutations for this one. We could generate the permutations manually, but again, I don't have the time and I don't want to do it. So we use a script. All the script does is it does that exact process that we described earlier in the presentation. It's going to plug the viable opcodes that you've defined into the various byte indexes starting at whichever one it determines as being the most feasible, in this case byte index 4, and it will generate all the permutations. So as we see, the first one for this one was on Wednesday, I believe this is the first one, Wednesday, January 21st, 4 p.m. At 1970. It was an EAX to EIP transition, and it lasted for 7 minutes and 9 seconds, as we saw. So let's watch out for this kind of stuff in October this year. Later today, I actually got to run at 2 o'clock, 36 minutes into the hour. I got to go take care of some business with some exploits that have to do with EAX to EIP transitions. So this just kind of gives you an idea. This is for the month of October, and I picked the ones that started during BlueHat and on. These are the viable windows. You can kind of see here that there is quite a big difference in time, and the gaps also get quite a bit higher. One of the next slides is going to actually be a diagram to give you guys a better feel for how wide some of the gaps are. So what I did is, using the output generated by that script, I went and plotted all of the various time distributions for the system time attribute for all the sets of viable opcodes that I took from the Metasploit opcode database. And what I saw here is you can just see kind of a unique distribution in the way that things are set up. But perhaps the most interesting one is you see the 2 spikes there between 2000 and 2005, the 2 big yellow spikes. Those are for ESP+8 to EIP transitions. And those are actually fairly interesting. So what this is in 2002 and 2003, this is system time attribute, or any other things that have the same attributes as that temporal address, had a huge jump in occurrences in ESP+8 to EIP transitions. If you take a step back, the dereferencing of ESP+8 is equivalent to a pop-pop-ret. And this is actually something that is very useful for people who are doing SEH overrides and things like that, due to the way that the stack is set up when an exception handler is called. So it's really, too bad we didn't know about this back then, because we could have had a heyday. Because think about this here. The whole point of this is that the system time attribute and the location that it's found is universal for every version of Windows. It's executable up until XPSB2 with hardware NX. It's just completely usable. So if we had this technique back then, we would have all these big time windows for doing pop-pop-ret transitions for our exploits. So if we had some vulnerability and we waited for the right time, we could just hit everything and not have to worry about version-specific targets. But the sad news is that a spike like this for this specific one is never going to occur again in the lifetime of anybody here. So sorry to disappoint, but maybe way into the future, however many 300 years it is, maybe they'll still be using this then. Who knows? But just to give you guys an idea of how big the spike was, in September of 2002 and in August of 2003, we saw the big spike up to, I believe, around 64 occurrences of both, and then it was done. So that was the interesting part. So at this point, I was just kind of trying to give you guys an idea of some of the stuff, some of the scripts and everything. So I'll pop this up here. The Chronomancer script. Let me make this a little bit bigger so you guys can see. Is that all right? Okay. Chronomancer script. This was written in Ruby. If nobody does Ruby here, I recommend it. If you're into object-oriented programming, it's pretty rad. But Chronomancer, pretty simple script. Basically, the purpose of this is to generate the permutations that to tell me the intervals for a temporal address with specific attributes. So, for instance, I can specify the period, I can specify the capacity, and then furthermore, I can specify the scale. And what the script will produce me is either, if I'm looking for the display the per byte duration, see how long it takes for each byte index to change, it will display that. And furthermore, it will also tell me all of the permutations for the viable opcode set that I specify. So for instance, down here, these are just some aliases that I've defined. So for instance, you see 4-byte capacity, period of 10 milliseconds, with absolute, measuring the scale since absolute 1970 epoch. So, I mean, when you run this script, if you say something like -a, 4 bytes, 1 second, period 1970, and you do -i, this is going to tell me that same thing that we saw on the screen. We saw that it was 1 second for byte index 0, 4 minutes and 16 seconds for byte index 1, and so on. But then if I want to, I can generate all the permutations. So I just hit this, and there's all the permutations being generated. It's CSV, comport into Excel, do all this analysis that I want on it, and that's that. So, and you can do this for all of these, all of the supported aliases and any of the other attributes of a temporal address that you would want. So that's just an example of a simple script, not very complicated, that takes the techniques described in the presentation to generate this stuff. Another interesting thing that I was going to show everybody was this other screenshot here. This is going to show the distribution. Let me see, I'll make this a little bit bigger. This is going to show the distribution for a temporal address that is a 4-byte temporal address, 1 second period, measuring the number of seconds since 1970 epoch. Just gives you another idea of the distribution of some of these instructions. You note that we don't see any ESP+8 transitions in this one. And the big reason for that is because this is a 4-byte capacity address. We really don't have the space to make this feasible. And furthermore, since the time t attribute is probably going to be signed, it's just we don't have the space for it. And you also see that eventually you have a register plus offset transition going up and down, and then it just dies off. Well, just kind of interesting to look at some of this stuff, see some of the generations. And you could do this for all of the temporal addresses out there. And the last thing I was going to show is attached to VMware here. And I was just going to kind of give you guys a concrete feel of what's going to happen if you look at shared user data in a debugger. So I'll pop into this here real quick. Give it a second to come up. So this will give you an idea of what it looks like in shared user data if you were to attach to the debugger. So I'm going to set my system time. This is just setting it to a specific time when I know that shared user data is going to, or the system time attribute is going to contain useful opcode. So if I disassemble 0x7FFE0018, that's 4 bytes into the system time attribute, I see a call EAX. So if I keep disassembling this, well, yeah, it's still this. If I go 4 bytes back, this is the start system time attribute. These are things that are changing every, less than a second. I keep disassembling it. Look at that. The instructions are constantly changing. There's no possible way I can make use of those. But if I go back, I see, oh, well, the call EAX is still there. Can still make use of it. So this kind of gives you a concrete idea of how the bytes that actually compose the timer state could be used for viable instructions. So that's that. Pop back over to the slides here. So conclusion. In general, if you're trying to use this as a person writing exploits and stuff like that, you're going to say, yeah, this isn't very feasible. I don't want to have to sit here for 3 days and 14 hours and waiting for this time window to come up where I can actually use this. So if you look at it from that aspect, it's probably not very feasible. The viable opcode windows tend to be spaced fairly far apart. As you saw on the table, they were spaced apart by days, depending on what it is, or even months in some cases. And furthermore, if you're trying to take advantage of something that has to do with system time, maybe there isn't going to be a way for you to get system time. So these different variables are things that might make it impossible to do this sort of stuff. So the list really goes on here. So the question is, though, what if you compromised an NTP server? This was a scenario that was suggested by Vlad902, one of the other Metasploit guys. He suggested, well, if you compromise an NTP server, you're automatically going to control the system time on the machines that synchronize to it. So if I set the NTP server to send a time to these clients that's going to contain these viable instructions, and I know that the system time attribute is located at this address, or some other temporal address is located at a specific address, well, I can make use of this. So furthermore, not only that, but you also are going to know which clients are synchronized. Since it's synchronizing over the network, you can see which clients are connecting, give them a couple seconds to update their clock, and after that, your NTP server is magically transformed into a worm distribution server. So that's a pretty feasible approach that you could potentially use to do this. So one other thing to identify here is, what are some of the mitigating factors of this approach? What are some of the things that make it so that you can make it unpredictable or not possible to do? Well, the first thing that we know is that the temporal address has to be predictable and reliable, the location that it's found at. That's the whole point. We're trying to find a universal or more predictable return address than the static ones. Well, shared user data is a great example. It's the same address, every version of Windows, every process, so on and so forth. So that is one of the very big mitigating factors. If the address at which shared user data was located was different between maybe an instance of a process or anything, well, suddenly this is no longer useful to us. So that is a very big mitigating factor. As I said, the capacity, period, and scale of the temporal addresses has to be consistent. If these attributes are not known or you can't determine them reliably, then you can't reliably determine at what point in the future you could make use of them. So that is a very important factor as well. If a timer variable is used, something measuring some system time, as I've said, you're going to have to know system time information. And lastly, this is a critical one, and this goes back to XPSP2 with NX support and all that stuff. The temporal address region, by default, it's going to have to be writable. Something is updating this address with new values constantly, so it is already writable. And furthermore, in order for this to work, assuming there's hardware-backed NX support, this address is also going to have to be executable. In all the versions of Windows prior to XPSP2 with hardware-enforced support, they are executable. I mean, they're inherently executable. Even if their pages aren't marked as it, they are inherently executable. So this is an important factor as well and can be a mitigating factor. So just to answer a question, and this is probably what makes the title a little bit weird, what's with chronomancy? This was suggested to me by a friend of mine, Richard Johnson, who just great word for describing this. Basically, if you go to the dictionary and you pop it up, I believe this has to do with some kind of magic stuff or something. But a chronomancer is basically someone who divines the right time to do something. And what better thing to do than divine the right time to exploit something? So that's why it's applied in this case. Wrapping up, if you want to learn more about this and you didn't think I did a good job explaining it, I have written a paper. Maybe I did a better job than that. You can go check it out, and the URL specified here. And also on the page, you can find the code for the implementation of the Telescope program and the Ruby script, Chronomancer, for generating the permutations and all the things of that sort. So with that, any questions? Yes?
So you find a location which has a call EX. So how do you transfer the execution to that?
Okay. The question is, you know the location of a call EAX, but how do you transfer control to that instruction? Well, it's very vulnerability dependent. If you're maybe doing a Stack Overflow or something, you're able to overwrite the return address. Well, you overwrite the return address with the address of system time, that call EAX, so that when the function returns, it's going to return into the call EAX and so on and so forth. So it's very vulnerability dependent, and it relies on whatever the thing that's arbitrary is the manner that gets you to that address, and then that address will get you then to your buffer or whatever the case may be. Yes, sir.
Did you find any longer than minute scale vulnerability? Are any measured in days or weeks?
Yes. The question is, did you find any time windows that were larger than minutes? And the answer is yes. The system time attribute itself, some of the ones that I showed there, pretty much all of them you'll find will be 7 minutes and 9-second windows. But there are some that come along that once enough time elapses, I believe it's on the magnitude of a year or something like that, you'll find ones that will last for 1 day and 6 hours. So it's very dependent on the 3 attributes of the temporal address. But yes, there are windows that will be longer than minutes and will be measured in days. So, yes? Yellow shirt?
Yes.
Yes.
It seems to me that it would work as long unpredictable as long as it's typically shorter than the duration of the opcode that you're interested in. It should still work.
Okay. The point is that you may, even if you don't know the period, as long as it's less than the duration of the opcodes that you would use, you could still feasibly use it. Potentially. The point is, though, that the period is used to derive the duration in this case. So if you could infer that the duration was a certain period of time, like maybe with a window, maybe sometimes it was 5 seconds longer, maybe times it was 5 seconds longer, you could just subtract that from the overall duration, and then yes, you could derive the other attributes and so on and so forth. So that is a case where if you have a potentially variable field, maybe just it differs by 5 seconds either way or something like that, you could still make use of it even though the period is inherently variable. So yes, good point. Yes, sir.
So all the examples are related to x86 architecture.
Yes.
Do you have any expectations or some comparison against different architectures?
Question is all of the stuff here is described for x86. Are there any parallels to other architectures? The answer is perhaps. The problem that you'll run into is going to be very dependent on the way that instructions are composed. For instance, if you're on Spark or some other platforms that have aligned instructions, so 4-byte aligned instructions or something like that, probably not going to be very useful for you for something that has a 4-byte capacity, because that means you have to fill the whole timer state. You aren't just using bytes that compose it. But perhaps if other situations occur, yeah, you could make use of it. I mean, this should be combinable to other platforms as well and other architectures. So, yes. Yes, sir.
Does this give you any particular advantages over other techniques where you might know data that's useful, like the results of some calculation?
Okay. Yeah, that's a good question. Question is this more advantageous or kind of has parallels to other approaches where you might know what certain data is set to in other locations in memory? And the answer is this technique is driven towards temporal addresses, yes, but the overall point is that if you can make use of some predictable location in memory that will be predictable, such as data, then yeah, I mean, that is something. If you know what's going to be the result of a calculation and you know what's going to be stored at a specific address, then yes, that could be just as useful. And then that won't be bounded by time, or may not be bounded by time. So yeah, that could be very useful as well. An interesting point regarding that was suggested by one of the other speakers a bit more, which is, maybe you could use something along the lines of system counters or something like that. Maybe there's a predictable system counter that at certain times is going to be set to a certain value. So that is a certain case that could be useful. Yes, sir.
So one other technique I've seen in the past is IP addresses.
Yeah. Yeah.
Have you explored that?
Have not explored that, but that is a good point. His point was that a certain piece of useful data may be IP addresses. Maybe if you know that the octets of an IP address are being stored at a specific address, then maybe you could make use of those. So yeah, very good point. Questions? Yes, sir.
How can we prevent people from using this technology for attack? Is the key that we should prevent something like buffer overflow so that people cannot write the return address? Is that the key?
Well, the question is how can we prevent people from using this approach? And the answer is, it's never simple, right? There are a couple approaches you could take, as you mentioned. Maybe we could try to prevent buffer overflows or something in general along those lines. Yes, if you prevent from the source, then yeah, all the things down the line will not be possible. But as we've all seen, preventing buffer overflows is a very, very hard problem. Still having problems with it today. But in terms of maybe mitigating this specific approach is, take the slide that talks about some of the mitigating factors. We saw that we rely on the location of this temporal address being predictable and reliable for whatever the targets that we're going to be attacking. So if that is a variable attribute at this point, then now no longer can we make use of this. So if we didn't know the temporal address was located at a specific address, or the address it was located at was pushed around between instances of a process, then no longer can we use this approach. So that's one way of doing it. Any other questions? Yes, sir.
You talked about the transition of the opcode EAX to EI.
Yeah. Okay. The question is, how does it transition, for instance, the EAX to EIP? How does that help you with an exploit? The answer to that question is, let's say when you trigger this vulnerability, you trigger the bug, you overwrite something, the register state is going to be of a certain setting, and it's going to probably be predictable. So, for instance, after your overflow occurs, let's say the EAX register points into a buffer that you control. So it points into my shellcode or whatever the case may be. Since I can control, in that case, I would want to use a state transition between like a call EAX, which will then transfer control into whatever the value is in EAX, and then take control of EIP, and now I'm running the code from my buffer. So that's basically the point of the transition, is the register would point into something that you control that you can then gain control meaningful execution flow. So, yes. Any other questions? Oh, yes, sir.
No, I think you mentioned that these were vulnerability dependent, or making use of these.
Yeah, I mean, this is, as with all things, the selection of a return address and things of that sort can tend to be very vulnerability dependent. If you're using the typical approach, static return addresses or something of that sort, you're going to need to depend on what the DLLs are that are loaded into memory. With temporal return addresses, the vulnerability in question, how you're overflowing the buffer is still a variable, but making use of these temporal addresses is still universal. So all you do is you plug them in as your return address or whatever it is that's getting control of execution flow, and that takes it from there. So
is it hard to figure out which vulnerability to use?
it's hard to figure out like which vector you're using to get control. It really just depends on the vulnerability in question. I mean, you'll get a pretty good idea once you start looking at it. You can say, oh, well, this is a stack overflow. I'm overriding the return address. Maybe I'm overriding the registered exception handlers. Things like that. Oh, this is a heap overflow. You'll get a pretty good idea real quick on what the type of vulnerability is. And then it's up to you to figure out a way to leverage that vulnerability into getting control of execution flow, which is the whole point of exploitation. So. Oh, what's that?
I think this is really a leading question about
okay.
Metasploit.
Yes, thanks for reminding me. One interesting thing that we've actually thought about doing in Metasploit is, taking what we've talked about here, and we'll plug something into Metasploit, where right now most of our exploits have, static return addresses and everything. They're relying on certain DLLs being loaded and target specific and yada yada. So wouldn't it be funny if we modified Metasploit to have target or time specific targets? So now all that you do is when you go to exploit something, you say, I'm going to depend on the time, and here's what I know the time will be on. This is what the current time on the person's machine is, and here's the instruction that I want to use, an ESP to EIP transition. So what Metasploit will do then is you'll say exploit, and it'll say, waiting 3 days, 14 hours, 2 seconds until the time occurs. And then once that time window comes up, kicks off the exploit, uses that temporal address, since it will now contain the viable instruction that you want to use it as a return address, gain control of execution flow, and bang. So that was just kind of a funny thing. May not do it, but just kind of a funny thing. Maybe we'll throw into Metasploit or something as kind of a joke. So any other questions? Yes, sir.
Well, as long as you were looking at the NT shared memory area, did you find any interesting opcodes that were not timer dependent, but seemed to be pretty much constant?
Good question. He asked, while we were looking at shared user data, did we find any other opcodes that might be useful for exploitation in that area of memory? The answer is, we've looked before. Some of the problems that you run into is, while shared user data is backwards compatible, it has to offset from previous versions of the operating system due to the fact that things will depend on it and everything. Generally speaking, we didn't find any that were particularly useful for exploitation. Like some of the stuff that you find in earlier versions of Windows 2000 and earlier versions of XP, you'll find that the instructions that are used to transition into the kernel for a system call or something along those lines will be found in shared user data. One of the reasons why it was executable, but now it's changed. But for exploitation purposes, unless you can get your register state set up in such a way that you can make use of it, doing a direct transition to a system call or something like that is not particularly feasible or useful. But haven't found any other instructions that you could actually make use of that would be actually useful for exploitation in the general sense. So, good question. Any other questions? Yes, sir.
For you to use this technique, you very much already have to control jump to this optical data. Given that you already have control quite control state, and you actually make the creative whatever point you actually have. Looks like the whole thing is like a secondary job.
Yeah. Okay, so I think, correct me if I'm wrong, your question is, why don't you just go right into your buffer? Is that right? Okay, so the question is, why don't you just return right into your shellcode, right where it's at? And the answer to this, not exactly a simple or obvious one, is that a lot of the times you don't know where it's at. if your buffer is on the stack or something like that, maybe you're in a threaded application, there have been lots of stacks allocated and deallocated and stuff like that, you don't actually know where your buffer is located. But you do know that it's located in a register. So by returning into instruction that makes use of that register in some indirect fashion, you then gain reliable control of execution flow rather than depending on a specific address that may not be portable and so on and so forth. So, good question. Yes?
Did you ever think about using this kind of approach to more advanced pieces of the PC, like the video card that nowadays usually has a constant rate to access their own readable and writable memory, to actually use that to go to the system?
Oh, are you talking about like shared video memory or something like that? The question is, have you looked at other like memory mapped segments or something like that that map directly to video RAM and stuff like that? Have not looked at it, but I mean, yes, that is one case. That, yeah, you could probably, if you can find, if you use Telescope, perhaps Telescope might find something in there. Yeah. So Telescope may find something in video RAM for the specific application that you could make use of. So yes, sir.
Similarly, there might be incrementing counters.
Yep. Yeah. Exactly. Yeah. The point was there might be incrementing counters, and yes, like the processor statistics and things like that, other incrementing counters, the number of seconds and program start, things like that. I mean, yes, at some point they will be set to a certain value, and you can make use of them. So.
And I think that's a great example. Brian Valentine kicked this off this morning and said, don't just stop at that specific case that the speaker's talking about. Think about your own product and what you're developing, and say, how does this technique apply to what I'm working on? So it's a great example of taking that back to your office, building 50.
Yeah, I mean, yeah, we totally encourage that. Metasploit is not, some elitist group where we're the only guys working on this. We encourage, everybody in the community, if this is something that interests you, play with it. Think about it. Think about other ideas. Shoot them over to us. Collaborate. That's what the whole point is here. So, and that's part of the reason why BlueHat's here. Collaborate on ideas. Get people thinking. So, yeah, good point. Anything else? Yes, sir.
Except jump ESP or push ESP, right?
Yeah.
Any other dangerous code that can be used?
Okay. Question is, other than jump ESP, push ESP, ret, are there any other dangerous opcodes maybe that you could use to transfer control? For that, I'd direct you and everybody else in the audience to go take a look at the Metasploit opcode database. These are just some of the instructions that we've identified that could be useful in exploitation scenarios. So, there are others. It just depends on the vulnerability. Depends on what the registers are set to, things like that. But yes, there are other ones that you could use. So
Matt, spend another couple minutes on that database.
Okay.
I think it's quite incredible that a bunch of volunteers actually went out and did this, and it's not just for one specific version of Windows, right?
Yes, correct. So to give everybody a brief background, the Metasploit opcode database, earlier in the presentation I referred to these static addresses, inside DLLs, things like that. The purpose of the Metasploit opcode database was to go and build this cross-referenceable database between different versions of Windows and different service packs. So we'll take NT, 2000, XP, 2003 server, SP0, SP1, so on and so forth. We'll take all of the default images that come with it, all the system images, and we'll run a scan on it. We will scan for all of those instructions that could be potentially useful for an exploitation scenario, and then we'll store those in the database. So then what that allows us to do is then when we're writing an exploit or something, we can then pop into WinDebug and we can say, well, this application has these modules loaded. Let's see what the opcode database tells me might be cross-referenceable, to make my exploit more universal, because the more I can use the same address across different operating system revisions, the more portable it's going to be, the less target determination I'm going to have to use. So this is basically a different approach to making return addresses more reliable. EI actually has also done a lot of research into this with their EE-REAP, which is another approach for kind of trying to determine reliable return addresses and that sort. So that's kind of the point. You can just go in, plop in your images that you have loaded, say which type of instruction you're trying to search for, and it will return you the ones and the platforms that they're compatible with. So that's the basic goal. You can find that on the Metasploit site if you want to check it out. Any other questions?
Elaborate a little bit, because from my perspective, it wouldn't take much to have some guy come in and extend Metasploit to say, you know what, here's the library of exploits that are in Metasploit today. Mm-hmm. Oh, and here's my opcode database.
Yep.
And here I've just done temporal return addresses to see which ones of these appear when.
Yep.
And then I've got this timer thing. So there's something that's sitting on your network that says, I know what these machines are, I know what they're vulnerable to, and I know what is going to happen at a certain point in time. You know, it wouldn't take much to make what is already point and shoot with Metasploit into something that is an order of magnitude different than that.
Well, you know, funny you should mention that. Metasploit 3.0 version we're working on now in the background that we haven't released yet is that we're actually planning on doing integration into the opcode database through some web services or something like that. So what will actually happen is exploits won't just have these hard-coded addresses that you're using for return addresses. Instead, the exploits will just say, these are the modules that are loaded. Go and find me a return address by talking to the opcode database and maybe pulling back and caching what the results are for that specific vulnerability. Tell me what return addresses I could use. And the interesting aspect of this is that no longer, right now in Metasploit, the return addresses that we're using are static. So if you're writing an IDS signature or something like that, maybe you could write a dumb one that says, well, expect this address, these 4 bytes at this specific offset in a packet. But now, if we do what we're going to call return address pooling, all that you need to do is, we're going to have a whole set of addresses that you could pick from. So now, instead of having just one return address for this target, now we have 50. So that is one of the things that we're going to be integrating probably from Metasploit 3.